The last thing I want to talk about is derivatives as rates of change. So one application of derivatives is to estimate an unknown value of a function at a point by using a known value of a function at a point together with its rate of change at the given point. So as long as we have a function defined on this interval from a to a plus h, the average rate of change is going to be the limit, and the instantaneous change is going to be the derivative. So for small enough h, we can solve to get the amount of change formula. So for example, we're going to use this to estimate f of a plus h. So if I have f of 3.2, that's f of 3 plus 0.2. So I can take f of a plus h, so 0.02, so a is 3, times f prime of 3, well, f prime of 3 is 5, so I have 2 plus 0.2 times 5 is 3. In this example, f of 10 plus 1 is f of 10 plus f prime of 10 times my h. So I have negative 5 plus 6 times 0.1. That gives me negative 4.94. So let P be the equation for population growth of a mosquito colony. The current population of the mosquito colony is known to be 3,000. If P of 0 is 3,000 and P prime 0 is 100, we need to estimate the size of the population in 3 days. So P of 3 equals P of 0 plus the derivative of P at 0 times 3. So I get 3,000 plus 100 times 3, so I have 3,300. We can use the derivative to analyze motion along a line. Remember, velocity is the rate of change of position, and if we take the derivative of velocity, we find the acceleration, which is the rate of change of velocity, and speed is classified as the magnitude of velocity. So here's some formal definitions. So if we have s of t is a function giving a position of an object at time t, the velocity of an object at time t is given by the velocity of t, which is just its first derivative. The speed is the magnitude of the velocity, and the acceleration is the double derivative of our speed function, or the first derivative of our velocity function. So, if a ball is dropped from 64 feet, the height above ground in seconds is given by this function here. So what's the instantaneous velocity? Well, for the instantaneous velocity, I need to take the derivative of this function. So v of t is the derivative of t, which is going to give me negative 32t. I need to know the time though. So what we need to do is we need to set this function equal to 0 and solve for t. Because I'm given a height, I don't know a time. So I'm going to subtract 64 from both sides. Negative 64 equals negative 16t squared. I get positive 4 equals t squared, so I have t equals 2. So then, if I want to know the instantaneous velocity at v equal 2, I plug it into this formula, and I get negative 64 feet per second. Now if I want to know the average velocity, that's going to be s of 2 minus s of 0 over 2 minus 0, which is negative 64 divided by 2. So the average velocity would be negative 32 feet per second. All right, class, so this next example is a comparison between acceleration and velocity. Remember, velocity is the first derivative of our function, while acceleration is the second derivative. So a particle moves along a coordinate axis in the positive direction to the right. Its position in time is given by the following function. I want us to find the velocity at point 1, and which is representative of time, and the acceleration at time equals 1. And we're going to use these to answer the following questions. So is our particle moving from left to right or right to left? And is the particle speeding up or slowing down? So I need to find the equation for velocity. So v of t is going to be the first derivative. So I have 3t squared minus 4. And my acceleration is going to be the derivative of velocity. So that's going to be 6t. I'm going to plug in my value for t equals 1. So v of 1 would give me a negative 1. And a of 1 gives me a positive 6. So because v of 1 is negative 1, which is less than 0, my particle on our coordinate plane is moving in the negative direction, so from right to left. And because my velocity is less than 1 and my acceleration is greater than 0, they're acting in opposite directions, causing my speed to decrease. And because of this, our particle is slowing down. Next, let's talk about position and velocity. The position of a particle moving along a coordinate axis is given by the following equation, when t is greater than or equal to 0. So the first thing I want to do is I want to find v of t. Remember, that's going to be the derivative of our function. So I have 3t squared minus 18t plus 24, and that 4 goes away to 0. When a particle is at rest, my velocity is 0. So I need to go ahead and set our equation for velocity equal to 0 and factor it. I'm given 3t squared minus 18t plus 24 equals 0. The first thing I want to do to factor this is pull out the greatest common factor. In this case, the greatest common factor of each of these terms is 3. So I have 3t squared minus 6t plus 8 equals 0. Next, to factor this, I want to find the factors of 8 that add up to negative 6. That's going to be negative 4 and 2. Let's move this over here so we have more room. So I have 3t minus 4, t minus 2 equals 0. Now I can use the zero factor property to set each of my factors equal to 0. And I have that my particle's at rest at t equals 4 and t equals 2. On what time intervals is my particle moving from left to right and from right to left? So I have at time 0, it's speeding up, so it's moving in a positive direction. Then from 2 to 4, it's stopping, it's at rest, so it's moving in a negative direction. And then from 4 onward, it moves in a positive direction. And I could have also found this by substituting in some points. V of 1, for instance, would give us 3 minus 18 plus 24, so that's 9, which is positive, right? And v of 3 would give us 27 minus 18 times 3 plus 24, which would give us a negative number, right? So this is how we know it's slowing down versus speeding up.